Hello and welcome back to this lecture on Foundations of Deep Learning. In this week, we will discuss practical methodology and the principle behind some of the basic CNN architectures that exist today. So we will first discuss normalization layers such as batch normalization, instance normalization, and so on. So these are very common to use in CNNs today, especially batch normalization layers. Next, we will look at transfer learning, which is also a technique that is very commonly used today. And after that, we will discuss some general methodology and debugging strategies that you can use while training these convolutional neural networks. Subsequently, we will learn about various parameter initialization strategies for the different layers that exist in CNNs. Then we will look at the basic principle behind some recent convolutional neural network architectures from AlexNet to ResNet and the more recent EfficientNet architecture. After that, we will briefly discuss object detection and semantic segmentation networks, specifically how these classification architectures can be adapted for these tasks of object detection and semantic segmentation. With that, let's get started.
Normalization layers in convolutional neural networks. Normalization is an important topic in deep learning, and getting your normalization right can be a critical factor in getting your model to train properly. The main idea behind batch normalization is that we want to have a unit Gaussian activation, so let's just force them to be that way. But how can we achieve this? Let's first consider a batch of activations at some layer. Now we have all our activations coming out, and if you want to make them unit Gaussian, we can just do that empirically by taking the mean of the current batch, and we can compute the variance and just normalize it by this. So instead of weight initialization, we are setting this at the start of the training so that we can have unit Gaussians at every layer, and hopefully this preserves during training. Now we want to make this explicitly happen at every forward pass through the network, basically by normalizing it by the mean and the variance at each neuron. So we look at the inputs that are coming into it and then compute the mean and the variance for the batch and normalize it by this. If you think of this, you can see that this is a differentiable function and we can backpropagate through this. If you look at our input data, we think of this as we have n training samples in our current batch, and each batch has a dimension d. So we're going to compute the empirical mean and the variance for each dimension, basically for each feature element. So we compute this across the current mini batch that we have, and we normalize it by this. So for whatever x was, it just makes sure that every column here is a unit Gaussian. We usually insert this batch normalization layer after fully connected or convolutional layers. The reason for doing this is that when we multiply by the weights in these layers over and over again, we can get this bad scaling effect. And this basically is able to undo this effect. One problem that you might think of is that it's not very clear if you want a unit Gaussian input to these tanh nonlinearities that we have. Because you'd like the network to basically pick whether it wants the tanh outputs to be more or less saturated. Now, we wouldn't be able to do this if we basically have batch norm at every input. One thing to note is that by backpropagation, it can happen that the gamma and beta end up taking the empirical variance and the mean. This way, the network has the capacity to undo this batch normalization. So that's why a batch normalization can act as an identity function. At test time for batch normalization layer, we take the empirical mean and variance from the training data. So we don't recompute this at test time, we just estimate this at training time. For example, using training averages, and then we use this at test time. We can apply this the same way to fully connected and convolutional layers. The only difference is that with convolutional layers, we want to normalize not just the training examples and independently for each feature dimension, but we want to normalize jointly across all the spatial locations that we have in our activation map, as well as all of the training examples. So we do this because we want to obey the convolution property, which means that we want the nearby locations to be normalized the same way. Here are some advantages of using batch normalization. So first, batch normalization makes the network easier to train, and it also improves the gradient flow through the network. Batch normalization works for more ranges of learning rates, and it allows the network to be more robust to initialization. So you can also think of the batch normalization as a form of regularization of the network. Okay, so when is it not a good idea to use batch normalization? So the first is when you have small mini batches. If the batch size is 1, then the variance will be 0. So batch norm cannot be applied. So it's not a problem if you have large mini batch sizes, but with small mini batches, the estimate will be very noisy, and this can affect the training of your network. So it's also not a good idea to use batch norm when you have recurrent connections, such as in RNNs. And this is because the current activations of each time step will have different statistics, which means that we have to have a separate batch normalization layer for each time step. So this not only makes the model more complex, but it forces us to use the statistics for each time step during training. So what can we do about this? Let's look at some other alternative ways we can perform normalization. First is layer normalization. Recall that batch normalization normalizes the input features across this batch dimension, whereas now layer normalization normalizes the inputs across these features. More specifically, in batch normalization, the statistics are computed across the batch and are the same for each example in the batch. Whereas in layer normalization, the statistics are computed across each feature and they are independent of other examples. Layer normalization has been successful in performing better in RNNs than in batch normalization. Next up is instance normalization. Instance norm is similar to layer normalization, but this goes now one step further in the sense that it computes the mean and the standard deviation and normalizes each channel in the training examples. So this was initially proposed for style transfer tasks, which is when you have an image and you want to transform it to another style, such as a different kind of painting, for example. So this addresses the fact that the network should be agnostic to contrast of the original image. And instance normalization is used a lot for this style transfer task. Most recently, instance normalization has also been shown to perform well for generative adversarial networks, which we will learn in the later lectures. Here is a comparison of the normalization layers that we've discussed. There's another one here, if you notice, that we call as group normalization. This computes the mean and the standard deviation over groups of channels for each training example. So you can think of this as being a combination of layer normalization and instance normalization. So if we put all the channels into a single group, then this becomes layer normalization. And if we put each channel into different groups, then this becomes instance normalization. So both layer normalization and instance normalization have not been demonstrated to be better than batch normalization for image recognition tasks, although they are more effective on recurrent neural networks. However, these group normalization has much closer performance to batch normalization, and in some cases, it even outperforms batch normalization for small batch sizes. Moreover, for tasks such as object detection and semantic segmentation, group normalization has been shown to be very effective. All right, so that brings us to the end of this video, and I have 3 questions for you. What are the 2 scenarios in which batch normalization does not perform well? And which normalization should you use for recurrent neural networks? Finally, which normalization has been demonstrated to perform well for the style transfer task? Now, I encourage you to pause this video at this point and try to answer these 3 questions, and we'll continue in the next video. Thank you.